Okay. So at this point, hopefully, I think everybody, for the most part, is registered for at least courtesy access and figured out what they want to do about books and stuff like that. I got a few stragglers in a couple of my classes, so you'll be getting messages from me. Don't be that person. Get it done. Get it done today if you haven't gotten it done. You can register, remember, for free, courtesy access for 2 weeks, right? And then you got to figure out how and what you're going to pay for and what you're going to do. And that includes your ebook, right, for those 2 weeks. So it's a good deal. Introductions, you should have completed it. The good news for you guys is you're my second class of the day, and last night I only got through my first class. So I haven't graded your guys yet. I had, in the beginning, tried to start grading, right, and then I got stopped. So if I graded you previously, right, and you didn't get all your points, you may have finished it since I graded, and I'm going to regrade it. Does that make sense to you guys? Make sure that you put your initial post, right, you explained your result, and you replied to at least 2 of your classmates so you get all your points. Okay? Look at the rubric if you're confused. Look at this recording I have right here on how discussion boards are graded. If I already commented on yours, if I asked you a question, please reply, right? And I'll comment on everyone's post this time, just, so that you guys get an idea and see how the comments work. When you go to your grade, you'll see a little box next to the grade, and that's where I've added a comment, and you can comment back. So if you have any questions on any of that and how to navigate, watch this video. So I'll be grading these this weekend, so get on it quick if you haven't done it yet. So I want to get caught up on my grading for the next round that'll be coming up. Okay, so we're in Module 1 still, right? We finished microbiology last time, so here's the 2 links to the lectures as well as the PowerPoint. Today we are starting the next topic, right? Today is the 28th. Right, so we're doing microscopy. Here's the PowerPoint if you wanted it before class. I ask that you watch this gram stain animation, right? And then, of course, after, I'll even post the link to today's recording, as well as on the front page. So, microscopy. Oh, did anyone have any questions before I move on?
I have a question.
Okay. Mm-hmm. Okay, let me open that one up to start. So I have a frame of reference. So she asked about, I think, the very first or second objective. Right, this one? Yeah. Okay, so define the science of microbiology and describe some of the general methods in the study of microorganisms. So this one's kind of goes through the whole lecture, actually, right? So when we define microbiology, what do you think of? Small, right? But then, as we continue throughout the lecture, and actually as we continue throughout this course, we're going to continue to talk about the techniques that are involved, right? So can anyone think of a technique that we talked about, an ability? They still aren't unlocking these doors? Thank you. So I'm looking for an answer from a student. Right, those are procedures, but what about like when we're studying microorganisms, right? So pasteurization, that's, so that it makes it better for us, but what do we need to do with organisms in order to be able to study them? Isolate them, grow them. Can we look at them under the microscope, but can we just slap them on a slide, throw them under the microscope and see them? Now we're going to fix them. We're going to talk about today, we're going to talk about staining them. So this objective is continuous. Do you see that? So the techniques we're going to continue to talk about, and that's why this is underlined. But kudos to your classmate, right, that said that I don't really understand that I've touched on all of this, and it's because one, we really haven't yet. Right? This one is a continuous one, and I didn't mention that. So thank you for bringing that to my attention. And sometimes, and you messaged me, did you not? Yeah, and you forgot to ask me yesterday, but that today's a good day. So a lot of times when you guys message me or email me, sometimes I'll say, ask me in class. Please try and remember to do that, because you asked a really good question, and I want the entire class to benefit from you asking that question, including myself, right?
You didn't go over Louis Pasteur or Joe's listing yet.
Yeah, I did really quickly at the end. You might have zoned out by then. I know many of us were like ready to be done. But very simply, so he asked about Lister. Remember, Listerine is named after him. Right? He's the very last slide in this PowerPoint. So actually, let me just end and fast forward. There we go. So there's Lister. Right? He provided indirect evidence. Unlike who helped us provide direct evidence that links an organism to a disease? Koch. And Koch's postulates. Right? Oh, yeah. So Lister, right, was instrumental in helping us with surgery, keeping stuff clean, cleaning instruments, cleaning dressing, cleaning skin, right? And because of that, we had a lot less post-operative infections. And so Listerine is an homage to him, right? That antiseptic we use for our mouths is named after him. He didn't discover it or anything like that. But he probably used a lot of the same stuff that's in Listerine, right, in helping his patients in this manner. And what was the other one, Tyler?
Louis Pasteur.
Oh, so Louis, there's a whole long list for Louis, right? So in addition to his help with the whole debate on spontaneous generation, right, he also worked with others. He helped us with vaccination and understanding this whole phenomenon is of attenuated, weakening organisms by growing them in artificial culture over a long period of time. And then that helped him and others develop vaccines for chicken cholera and anthrax and rabies. And we talked about this. I remember this. Right? And then also he was a major contributor to the process of fermentation as it relates to making alcohol, right? Wine and things such as that. And he developed, of course, the process that's named after him of pasteurization, which we'll talk more about later too. Okay? So you guys should be, as soon as you can, right, be reviewing this material, making sure you have an understanding of it, right, of all these objectives, right? You have your list of objectives, and we go through them in every single lecture that I give. Once you feel comfortable on a topic, what should you do to test your knowledge? Right? Go to Connect and do the assignment linked to that topic. Right? And I'm putting these links like everywhere for you guys, right? They're in here, right? They're on our modules page, right? So there's a Connect link. And that's going to take you directly to Connect. You don't have to sign in once you've already signed up, right? You just click Connect. And then it has the list of assignments, right? And this one is just to make sure that as you experience, and actually I'll pull up this one. So 11 students in progress, 15 not started yet, and 9 submitted. So pat yourself on the back if you're one of the 9. So some of these, like this one, because you're actually dragging and dropping things, run on software called Flash and things like that. So that's why that software check one I have like some of these drag and drops, and I have some of the animations built in, so you can check and make sure if you're not seeing stuff or not being able to move stuff when you go to do an assignment, it might be because your computer doesn't have the necessary software. Does that make sense to you guys? Right? Or even the program you're using, like what web browser you're using. Remember, for Canvas, they tell us not to use Internet Explorer. Use something other like Google Chrome or Firefox. Okay? because then you run into issues like this. So this, of course, is saying the answer. I didn't click my student view.
That particular table that you just showed,
Mhm.
if those weren't in exact order, it was wrong.
Right, yeah, you have to put them in the right order. So notice just like my tables, this one doesn't actually have like off to the side here, but you can tell by this one, they're talking about cells, right? So usually single-celled, so you got to look for the other things that match up, right? So what else is, all right, so it can be single-celled or multicellular. Who's that? Eukarya, right? So that where some of you guys might, I think one of my students from last semester, remember I said they complained there was something wrong with this assignment. I think he wasn't lining them up right. Does that make sense to you guys? So no nucleus.
But like if there's two, like the two under eukaryote, they have to be in order. Like I couldn't figure out why it was wrong at first, and then I just switched them around and they were right.
Yeah. So, little glitches like that. The good news is for testing, I can't do this type of questioning. So it'll be matching, true and false, which I do very few of those. I'm not a big fan, but I'm required to. Mostly multiple choice, right? Okay, any other questions related to this kind of stuff? All right, I'll go ahead and move on. So go to today's lecture, microbiology. Microscopy, sorry. So we're going to start talking about microscopes. So you need to be able to identify, and so of course think about how these objectives are written and how they would be asked as a multiple choice true and false or matching question. Thank you. Okay, so we need to know the importance of contrast, magnification, resolution, numerical aperture, and refractive index as it applies to microscopy. So, of course, we have to know what each one of these things are, right? So we might want to start with defining them, right, before we can identify their importance. So for magnification, what is that? What does it mean to magnify? To enlarge, right? Do we actually enlarge the actual specimen? No, just the image of it, right? So it is the process of enlarging something only in appearance, not in physical size. I love my son all the time with his homework packets. He's like, the copy machine messed up this one. I said, no, honey, the copy machine did not mess that up. What's written on the page, it just copies. What was originally on the original page was wrong. The copy machine did not change it. It just copies, right? So we're just enlarging, right, in appearance, not the actual thing. So I think we looked at this one last time, that really cool website here, right, where you can go through and go all the way down to a single atom, a carbon atom. And so when it comes to microscopes, though, the importance of magnification is that unfortunately we have some limitation with the types of microscopes that we use because of how they work, right? So for light microscopes, which utilize light, to stay in the visible light spectrum, we're limited. We can only get so good of an image, we can only magnify so much and be able to see it using visible light. So about as small as we can go is around the size of most of your bacteria, right? Viruses are not in that range, right? But of course, we can go all the way to 1,000 times magnified, right? And some microscopes higher and see, you know, bacteria like streptococci and E. coli and rickettsia. And we can very easily see, as those of you guys in microbiology lab right now, see eukaryotes like amoeba, right, and red blood cells. You need different microscopes like electron microscopes, which of course you'll still be able to see the large stuff in even greater detail, but then you actually are able to resolve some smaller things like viruses and proteins. And then the really cooler, newer microscopes that work with atomic force can see right down to the atomic level. Now, of course, you're not actually seeing, per se, again, an image is produced for you, an appearance, a computer graphic that is showing the information that the microscope is able to deduce from the specimen. A lot of times these images, and we'll look at some of them, are colored. And they do that to denote different things, not that the organism or the molecule has that particular color. Does that make sense to you guys? It's much easier for us to understand and look at an image that's in color as opposed to in black and white, right? Speaking of black and white, do you know people who that are colorblind, the world is almost like black and white for them, right? They have special glasses now you can buy that correct for color blindness. How freaking cool is that? And again, it has to do with the properties of light and how things are interpreted by our brain, right? So the cells in the eyes of people who are colorblind, they don't have enough of the different types to detect subtle differences between colors like red and green. And there's different variations of color blindness, so it is almost just like a prescription, like for glasses that account for your lenses in your eyes being able to focus properly. So it's pretty cool stuff. A friend of my husband's got a pair from his girlfriend for Christmas, and you see him in the video, he's like looking at a roll of green and red wrapping paper for Christmas. He's like, wow, I can see it! It was really cool. I was like, wow, what can we can do just about anything nowadays. Amazing. Amazing. So here's good old black and white, right? So these are electron micrographs. These electrons are detecting the differences in the organisms and generating these images for us. So, you know, the light and the dark mean different things and help us be able to visualize. This is one of my favorite viruses. These are This is viruses that attack bacteria that we'll talk about, typically referred to as bacterial phage, or just phage for short. They look like little spaceships, huh? And they literally like land on the surface of bacteria and inject their DNA or RNA into the bacteria. It's pretty cool stuff. These are bacteria over here, right? And this is a different preparation where they've literally cut through layers so you can see inside the cell. So there's the cytoplasm, the plasma membrane, the outer membrane, and even another layer. I don't know what S stands for. I didn't put my thing there. And you can see the flagella on this one and the little tiny fimbriae. And these are things that for bacteria, again, it's too tiny for us to see these types of things with our light microscopes, right? To be able to visualize and study stuff in much more detail, that's been made possible by the advent of things like electron microscopy. So magnification really can tell us so much more than what we knew previously. So it can be very important. And notice that on these pictures, do you see this bar? Just like on a map, like they'll have a bar and it'll tell you it's so many feet or miles or something like that. In this case, again, this is a length. This lets you know that how big what you're looking at is as compared. So this is 100 nanometers, y'all. Right? So millimeters, right? Imagine millimeters on a ruler. I want to say this is 1,000 times smaller than that. Right? I should know my units, huh? I'm a cheat. That website has the conversions. There it is, right? So micrometer, right? Millimeter, excuse me, micrometer is 1,000 times smaller than a millimeter. A nanometer is 1 billion times smaller. All right, to give you some perspective. Millimeters you can see, Micrometers you're not seeing, nanometers you're not seeing without microscopes. Right? We can go to about 200 nanometers. You can see something that small with your microscope in lab at oil immersion. So, right? So this is micrometers, right? So that's big enough, right? We saw Amoeba yesterday in lab, and we'll see it again today in lab. Paramecium, right? You can see a human red blood cell. That's 8 micrometers. I don't know why that one's not coming off the tongue, right? These guys, we're still in micrometers, right? We can go down to nanometers with our microscope. So again, micrometers, we can see good old E. coli. That's about the limit of our resolution, though. Couple micrometers. So the next problem we run into is being able to actually see them. So not all organisms have natural, what we call contrast. What is contrast? Coloring, right? So it's the difference in color and light between parts of the image. So even though this is black and white, right, this one, it's different shades of black and white, right? And then, of course, color is best, right? We all love color. They even have adult coloring books now. No, they really do exist. I'm not kidding you. They're great. They're great. Coloring is awesome stress release, y'all. If you're in A&P, they got the A&P Anatomy and Physiology coloring book. I highly recommend. We can't color our bacteria, though, can we, on our slides? Not with colored pencils, anyways. What do we use? We use stain. We use dyes. Right? So a lot of the microorganisms that we work with don't have natural color to them. They're translucent. So you just slap them on a microscope slide and throw it under the microscope. You ain't going to see much of anything. Right? So we have to create contrast by staining them. So you do a lot of staining in microbiology lab. That's coming. Right? But some microscopes do have the ability to help create and contrast with different filters on those microscopes. But the most common way we create contrast, these differences in color and light, so that we can visualize our specimens, is through staining. So the Gram stain is the most widely employed staining procedure in microbiology, and depending on the cell wall structure of the bacteria or the cells themselves, they'll come out one of two colors, either purple or pink. Purple, if it stays purple, is said to be gram positive. If it loses the purple color, gets decolorized in the process, and then gets stained with the counter stain, safranin, which is a reddish dye, they actually appear pink. And those are our gram negatives. So the positive and negative is a result, right? Did it stay purple? It's positive. Did it decolorize and get stained pink? It's gram negative. Acid-fast staining is another differential stain, not as widely used as the Gram stain, because very few organisms stay stained the acid-fast stain. And there'll be a reddish purple, you can see them here clumped up, where the non-acid-fast, the ones that didn't stay stained with the initial stain in the acid-fast procedure, will be a different color. In this case, they're bluish, but it really depends on which staining protocol you use. There are different methods out there for acid-fast staining. All of them, though, use the same primary stain. So your acid-fast organisms are always the same color, this fuchsia purplish red color. Same holds true for endospore staining. So obviously, again, this is a special technique to be able to stain endospores if they're present so we can see them. This particular procedure, the endospores are in red, these little dots, and then the cells you can see are kind of this bluish color and really just outlined in blue. But there is a different endospore procedure we use in lab where the cells are going to be red and the spores are actually going to be green. So it's important to know, right, your procedure and what results you expect based on the procedure you're doing. But again, we're utilizing color here, and actually even multiple colors, to be able to distinguish different things about what we're looking at. All of these we're staining the cells, as well as down here. Down here they're just using a single stain, so a single color. Crystal violet, which is kind of a purplish color, or methylene blue, which is kind of a bluish color. This staining procedure stains the background and not the cells. The cells are actually clear, which is hard to see sometimes because other crud on your slide also won't get stained. But right here you can see these are bacteria. This is a bacteria shape, right? Here's 2 rods. Here's 2 more. Here's a couple more over here. These little round specks are probably just debris on the slide. But again, we can visualize something. We've created some degree of contrast. Resolution is also important. This is the ability of the microscope to separate or distinguish between small objects that are close together. And in that, it's going to help you be able to easily visualize stuff. So I always use the example, too, of our, everyone's got a camera phone nowadays, right? Depending on how much information your device can store will determine how much you can blow up that image, right? If you don't have all the little individual pieces of information, then when you go to blow it up, it gets really blurry. And that's referred to as resolution as well. And again, it has to do with how much are you packing in there, right? So when we put things really close together, Ashante, can I pick on you? I can't remember if I can pick on you. Do you need those glasses, those beautiful glasses to see me? Yes, I did pick on you already, right? And you sat in the back of the class today. Thank you. So go ahead, take your glasses off. Don't tell her. How many fingers am I holding up? All right, put your glasses back on.
Oh, no.
She really needs those glasses. All right, so 4. What was the problem for her? Resolution in the fact that my fingers are close together, right? If I'd done this. Go ahead, want to try it?
Let's see. 4. 3.
All right. Helped, right? So, you know, resolution, again, it has to do with this closeness problem, right? So different microscopes can help with resolution, and it really depends on the type of microscope you're using, too, at what level of resolution you're going to be able to achieve. So as you can see by these 3 different images, these are all a euglena, cute little protist here. He's got chloroplast, and he can swim around. This is the exact same specimen, 3 different microscopes. This is a light microscope like we have in lab using what we call bright field microscopy, where you can see the background is quite bright. And the reason why you can see him is he has natural colorization due to his chloroplast inside. This is dark field microscopy, where the light has been shined at an angle instead of up through, so the background is dark. This one is phase contrast, as the name implies, right? We're creating more contrast, in this case by using special filters that affect the wavelengths of light utilized by this type of light microscopy. You can see much more detail here, right? Even in the organism, and you're like, oh wow, look it, there's stuff outside of him, right? There's actually another organisms swimming around this euglena. Which here, you're on this slide, you're probably like, oh, that's slide crud, right? This one too, you're like, oh, there's just some crud on my slide, right? Here you're like, oh no, wait, let's look at this again. These have shape to them. There's a lot of them, right? This might be something else, and it is, right? So resolution can really affect what we're able to see, how clearly we can see it, whether we can resolve it as seeing it as separate. Right? Here it's just like, okay, that's just a blob. When you look closer, you're like, oh, a bunch of little organisms. There's a difference in resolution here. So resolving power, or the limit of resolution, can be calculated. This is the minimum distance, right? This distance right here that has to be there for that microscope under those conditions be able to see it as two separate objects, right? So for Lashante, right, I got to have them apart, not close together. She's not going to see it, right? Her resolution for her natural lenses in her eyes can't do it. Your eyes, that lens in your eyes, you can adjust, right? Microscope lenses, eyeglasses, right? They're stuck at a particular resolution or ability to focus light and help you be able to resolve and see things. The good news for those of you guys that are in lecture and not lab, you do not have to memorize or calculate this formula. Those of you guys in lab do, right? It's on the quiz. So it's the wavelength of light, right? We're very limited. Again, when we're dealing with light, right, we're restricted by that. And then, how powerful are those lenses, right? Those lenses have a set, you could say, prescription. That's known as its numerical aperture. And if we know what that numerical aperture is, we can figure out what the resolution is for those conditions. How close, right, could we put them together and you would still see them as separate? Any closer than that, they're going to blur together and you're not going to be able to resolve them. So on your microscopes, it tells you for your lenses, and these are objective lenses, you can change out between them. It tells you the magnification power, that's the X times magnified. Next to it, the 0.4 that you see here, that is the numerical aperture for that lens. Right? You could use that, and depending on what filter you're using, what wavelength of light you're using, you could figure out what your resolution would be under those conditions. How close could things be together and you'd still see them as being separate? The good news is that when we go all the way to oil immersion, which isn't shown here, that objective lens, it's about the resolution of the size of our bacteria, about 200 nanometers. So we can see them as separate, right? They don't blur together. We can see individual bacterial cells. If we couldn't, obviously we wouldn't use them. But we're right within the limit. So this numerical aperture is the property of the microscope lens that determines how much light can enter and how great the resolution of that lens can be. Depending on what you're trying to look at, right, will determine whether the microscope you're using is useful or not. So obviously these are factors that scientists have to take into consideration, right, when they're trying to study something. Do they have the proper equipment? Right? Pretty soon here at Delgado we're going to have an electron microscope. I'm so excited. Right? Oh, the reason why we haven't gotten it yet, it's going through the process. You know how that goes. Like 20,000 people have to sign off on it, and then it actually has to get delivered, and then it has to get set up. And I don't even know if they have a room assigned yet. So yeah, there's multiple factors. But we get some really cool equipment in already. Pretty excited. And I'm going to write a grant coming up. I want to try and get us a phase contrast microscope. So, but I think the Zoe that they got in, an imaging device, can do phase microscopy in the biotech. So I'm signing up for that training day when it comes up soon. Can't wait. New toys. So refraction is another problem that we deal with, especially when you're dealing with light. So this pencil in this glass of water almost looks like it's broken, right? But we know it's not, right? It's kind of like our eyes playing tricks on us, or the fact that light moves at a different speed through different media. And what we mean by media is air versus water versus glass. So as you can see, right, it's going through glass and water here, but just air and water here. That difference in speed gets the image to us at a different rate, and so they don't match up, hence the shift. This creates a real problem if you want to spear fish, especially if you're not in the water. If you're above the water, right, you have this same problem. The fish is going to look like it's here, but in fact, it's down here. And you have to be able to adjust for that, or you're going to miss the fish. If you're in the water with the fish, right, same media, not a problem, other than the fact that, the sucker's moving. You got to kind of judge on, where he's going to be after you shoot. You kind of have to shoot ahead of him to get him. Make sense? So how does this apply to microscopy, though? We put a glass slide on a stage, right? Light goes through it, and then to the lens. What is it traveling through in between the slide and the lens? Air. So refractive is the measure of the relative velocity, right? How fast the light is moving as it passes through a medium. And it's different, right? If it's going through glass or water or air. Air's the worst, because it also has scattering problems, not only speed. So how do we fix this, y'all that have taken lab? We put some oil on the slide. So at the very high magnification of 1,000 times magnified, our objective lens says oil on it. The reason being is that you need to put a drop of oil on your slide. This will fill the gap between the objective lens and the slide, or the cover slip of that slide. This will help focus the light and keep it moving at the same speed into that lens, so you can clearly see your image. The oil we use has a similar refractive index to the glass slide. So again, it keeps going at the same speed, straight into the lens, for help you visualize it. Many beginning microbiologist students say, Miss Erica, I can't see my slide. And I go, all the way from the other side of the lab, I know they can't see a darn thing. Why is that? Because there's a big old gap between the oil objective lens and their slide. There should never be a gap there. It should be a tiny little gap, and what should be filling that gap? The oil. And I'm not saying dump a whole bottle of oil. You really only need a good-sized drop. Right? And if you are truly in focus, that objective lens will almost be touching that slide, and the oil will be filling that gap. If you're not in focus and you're way out of focus, don't go to high dry, because you're going to pick up oil, right, onto that lens from the slide with the high dry. High dry is only 400 times magnified. It's a waste of time in microbiology lab when you're looking at bacteria. It's not enough magnification. So go around the other way, right, past scanning, go back to low power, 100 times magnified, focus it up there, swing back around the other way so you don't go through high dry, go back to oil immersion, and find focus. And bam, there you are. You also don't need to keep moving your stage up and down, right? Just move your objective lens to scanning the little red one that we don't bother looking through all that often because that's only 40 times magnified. It's like a waste of time in microbiology class. But guess what? There's a big gap between that lens and the slide. Just slide your slide off, slide another slide in, and then go to low power, right? Focus at low power, move it out of the way, put your drop, put your oil immersion in place, fine focus, bam. You can get through a whole tray of slides like that, right? Once you got your stage focused, don't move it. Just move the objectives out of the way so you can get your slides off and put the next one on. Right? You'd be Speedy Gonzales in the microbiology lab. Right? And then when we're done, we wipe the oil off the lens because over time that oil will creep into the housing of the lens and get behind the lens. We can't clean it then. The lens becomes permanently blurry. This is what's happened to 90% of the high dry objective lenses in microbiology lab. Students didn't clean them off when they got done. The oil creeped in, and I guess they don't seal those as well because you're not supposed to put oil on them, right? So it always gets in, and then you have a permanently blurry high dry, which I haven't bothered replacing them because we don't need them in microbiology lab, right? You can just go from low to oil immersion because our microscopes are what are called parfocal. Anyone know what that means? It'll stay in focus between the objective lenses. It's not, you're not going to have to do large focus adjustments. Hence why you can go from low to high, right? Oil immersion, high, and just fine focus and not coarse adjustment. So what kind of cool things can you see? Well, it depends on the microscope, right? And the ability of that microscope and what type of specimen you're looking at. So this amoeba looks pretty cool. He looks like he's going to get you, huh? He's going to have us for lunch. This is differential inference contrast microscopy. It allows you to see stuff almost three-dimensionally. And again, it's a contrasting microscope, so it's utilizing special filters. So they don't have to stain the organisms, and they create this large degree of contrast. You can see all the little stuff inside this guy. You can even see that, you know, this is kind of further back, and this is coming out at you right here, and this may be further back. You can kind of see the whole amoeba. He's not all in focus, right? The parts that are further away are kind of blurry. But much greater depth of field, right? You're seeing more of the organism than you would with a standard light microscope like in lab, right? So some of the specimens that we look at are really thick, like Spirogyra. That's a really thick algae. So you're not going to see sometimes the whole fiber in focus because it's not in the same focal plane as the rest of the organism. Right? So you got to focus up and down to see the different parts, right? And other parts are going to become blurry. And this is going to get even more of a problem as you increase in magnification. Because as you increase in magnification, your field of vision, right, how wide you can see, gets smaller. So anything you want to look at, you better put in the center before you go up in magnification, right? Because it might be gone. And your depth is going to decrease too. How thick you can see as you increase magnification. So microscopes like this one that can help you with that problem. You can see more depth, greater resolution. So it almost looks three-dimensional, which the organism is, right? Organisms are not flat, right? They're three-dimensional. And you can see in greater detail with this contrast. And the great thing about contrasting microscopes, you can create contrast with the special filters, right? As opposed to staining. So if you stain an organism, what typically happens to it? It brings it in and it kills it, right? I always think of, oh my God, when I was in college, some fraternity decided to paint one of the swans pink. They killed it, y'all. And swans mate for life. The one that's left, he is not in a good mood. He is evil. And you kind of can't blame him because they killed his mate. I don't know if it's a male or a female. I never did find that But there's one left, and it's not happy because it's all by itself, right? Staining kills, dyeing kills, right? Unless you buy the safe stuff, which apparently they do have for animals, right? So those people who paint their dogs and stuff, hopefully they're using the good stuff. Mardi Gras coming up, you see some strange stuff. This is New Orleans. Forget about Mardi Gras, it's all the time, right? Yeah, that lady in Goldfinger, like they painted her in gold for that movie, what's that movie? Bond, right? James Bond? One of the James Bond movies. They painted her all in gold. She almost died because she couldn't breathe. So, yeah, be careful. I wonder about those guys who paint themselves silver and gold down in the French Quarter. I guess they did, well, they painted her whole body. You know, they don't paint their whole body, so I guess they're okay. But, yeah, you can suffocate yourself doing that. Not a good idea. So, think about our poor microorganisms. When you stain them, what are you doing to them? You're killing them. So, if you want to see this awesome amoeba move, you can't stain it, can you? So, how are you going to see it? You got to try and create contrast. In the case of our microscopes that don't create contrast with special filters, you got to play around with light, right? You got to make it a little darker, a little shadowy to be able to see it. Anyone know what type of microscopy this is? It says it on the page. Who can read today?
Fluorescent.
Fluorescent, right? So this is organisms. Some of them are naturally fluorescent. Others we can dye with fluorescent dyes. Very popular technique now in microscopy. Very widely used. We can actually use special dyes that will specifically adhere to certain components of cells. It can tell you whether the cell was alive or dead when you stained it. Notice I said when you stained it, because once you stain it, you just killed it. Right? So when you stained it, this one was dead and the other one was alive. It's a different color, but now they're all dead. And this type of microscopy uses UV light. Do you want to look at UV light? No, that'll damage your eyes. So again, it has to have special filters so you don't damage your eyes when you utilize this type of microscopy. It can be very beneficial because, like I said, we can buy dyes that specifically attach to specific components of cells, can tell you information like living or dead, whether it has a particular substance or not. They can use it, say they take a bacterial smear from you and they want to know if you have strep. They could use a special dye that only adheres to Streptococcus prurigens, which causes strep throat. So they can use it at the diagnostic level.
When you dye cells and it kills them, do they look different when they're dead under a microscope?
Death does affect them a little bit. So she asked, do they look different when they're alive or dead? And yeah, their slides will vary slightly between living and dead and other components. But usually, again, the level of study that you're doing in a microbiology lab is not going to affect your results. But yeah, they do get changed by the fact that they are dead and no longer living. One thing, you stop what when you're dead? Living and moving, right? So like motile organisms like amoeba, right? If you stain it, it ain't moving anymore, right? So if you want to observe motility, you can't stain it. You've got to find some other way to see it without staining it. And in a microbiology lab, we'll look at bacterial motility, and we're going to, again, play around with light in order to achieve contrast to be able to visualize them. Because if we stain them, we'll kill them, and guess what they'll stop doing? Moving. Right? Electron microscopy, again, nothing's alive. Right? We're shooting electrons at them. We're basically very similar to X-ray. Right? And again, we're creating a computer image. There's different types of electron microscopy. One where we can slice the specimens really thinly. Others we can use a much larger specimen and we coat it. Typically they coat it in gold or metal. And we can get more of a three-dimensional image produced. And that's scanning electron microscopy. That's what these images are. And again, you can usually tell if it's an electron microscopy image because they'll be black and white. But sometimes they color them. Just like in the old days, remember they'd take black and white images and then they would color them by hand? Right? So sometimes they'll do that. They'll take an image and they'll color it to help point out what it is they want you to see in the image.
Wait, that's 3D again?
Yeah, see how it's three-dimensional? Because this is scanning electron microscopy, as opposed to transmission electron microscopy, which you have to have thin sections, and it transmits through. Where this scans, right, the surface. So this one is, did I put a label on it? Darn it, I didn't. This one uses lasers. I've actually used one of these. LSU Vet School, it's got some really cool microscopes. And this one, because of it uses lasers, and it can generate on the computer three-dimensional images. And again, they use special dyes so they can visualize different parts of different cells and everything. It has its own special room and its own air conditioner, which is kind of cool, right? Because you got to keep it cool, right? Because of the lasers. You won't find it. It's a room within a room within a room. They keep it hidden. It's a very expensive piece of equipment. You can't get into LSU Vet School anyways. You can't just walk in. They have security. So this is one of those newer high-tech ones I haven't gotten the chance to play around with. And again, similar to electron microscopy, it's going to be a computer generating an image. Again, the colors here are ones that are imposed by the program to be able to help you visualize the different components. This is actually, 3 turns of DNA, right? You see the alpha helix? So right down to the atomic level, right? Pretty amazing stuff. My next sabbatical. I want to spend a summer playing with one of these. That'd be cool. So more from those types of atomic force microscopes. So again, right down to the atomic level, we can see the molecules making up the pores in this membrane. So as we've said, right, why are we going to stain? Stain is going to help us visualize. But it can tell us so much more than just what shape is it. We can do specialized stains like the gram stain and the acid-fast stain and the endospore stain and the capsule and flagella and actually be able to see these structures if they're present or know whether it has a particular cell wall structure or not. So simple staining is just that. Just one dye. Oops, I don't have my answers. Nope, sorry. So a simple stain is just using one stain. That's it, just one. So why do we stain them? So we can what? So we can see them. So here's some pictures, right? And there are 2 primary different types of stains that we use. We use basic stains and or acidic stains or dyes. Basic stains have an overall positive charge. Acidic stains have a negative charge. And as we know, charges interact with each other. Who likes each other? Negative and positive, right? The old saying, opposites attract. That's how I always explained my first marriage. Right? So, most of the stains we use are basic stains because they're positively charged, and our cells are mostly negatively charged. Your membranes, your nucleic acid, your DNA inside the nucleus, highly negatively charged. So, attracts those positive basic dyes a lot, right? Stains really well. So most of the stains we use will go right into the cell and even stain the cell's membrane. So you can see the whole cell is stained in these two pictures, right? That's because crystal violet and methylene blue are basic stains. Very commonly employed stains used in microbiology. Acidic stains, on the other hand, are negatively charged, and if the cell is negatively charged, what problem do we have? They're going to repel each other, right? That cell is not going to attract the dye, instead it's going to repel it. So it's like when you try to put two magnets together the wrong way, you put in the two positive or two negative poles together, they just keep flying apart. That's what's happening here. So instead of the cell being stained, what gets stained in this picture? The background. So this almost looks like dark field microscopy, right? Because the background is dark. But it's not. This is actually what we call negative staining, where you stain the background. Again, you're using a negative acidic dye. In this case, the dye happens to be black. It's called nigrosine. There are other acidic stains. They're not as widely used in microbiology because, again, what are they going to stain? The background, the slide, not the cells. But sometimes we need the background to be stained, right? So sometimes we do employ acidic stains, right? And we stain the background.
So the acidic is the background, so the basic will be the positive, which will be the image that we use.
So again, what can you tell me about these organisms? What does it allow us to see?
The shape.
The shape, right? How they're arranged. Like, see how these two guys are next to each other? But yeah, it pretty much stops there. So although you guys are going to do some simple stains like this where you use just one dye, whether it be a basic or negative in lab, these aren't as widely used in different clinical or research settings because it doesn't give you a lot of information. You can get this same information using staining procedures that will tell you even more information. And those would be the differential or the specialized stains that we're going to talk about next. So what is a differential stain? Yeah, differentiate means what? The differences, right? So we're going to be able to group organisms based on their differences. The difference here, since we're dyeing, what's the difference going to be? Color, right? You're going to get different colors. Like I said, with gram stain, you get purple and pink. With acid fast, you're going to get that carbofusion purple, pink, fuchsia color, and some other color, right? The things are going to be different colors, and that will help you differentiate. So for the gram stain, we're going to see purple or pink, but that's going to mean something to us. And you can see what shape they are, right? Look at, there's some little squiggly ones in here. Right? And some rod-shaped here. Here, again, rod-shaped. Little endospores. So these allow us to see the cells, but also know something based on the color of the cells. So we'll go into, for each one of these stains, right, what it is we're seeing and why. So this is a to be continued. For acid-fast staining, we're typically doing this stain when we're looking for a particular genus of bacteria called mycobacteria. And these guys stain that purplish pink carbofusion color, that fuchsia color, because they contain mycolic acid associated with their cell wall. Hence their name, myco. And they also look like fungi, right? They're rods, but they'll clump together. And they'll form masses almost like the filaments that you see in fungi, right, in molds. But they are, in fact, bacteria, hence the bacteria in their name. Capsule and flagella stains. The stain name tells it all. What are we looking for when we do a capsule stain? A capsule. What are we looking for when we do a flagella stain? Flagella. So why do we need these special stains to see these structures? Right? Yeah, we can't see them without these stains. So we'll start with the capsule first, right? And these happen to be yeast, but bacteria, a lot of bacteria produce capsule too. So here's the cell. You see the cell inside? This clear halo around it is the capsule. And then what do you notice about the background? It's black, it's dark, right? This is not dark field microscopy. This is bright field. This is because we stained the background. The reason for that is so that we could see this unstained capsule. We don't have any stains that will stain the capsule. So we've got to stain the cells so you can see them and the background. And if it has a capsule, it'll be unstained in between the cell and the background. So we need to use this special staining procedure to be able to visualize these structures. To see capsules, we got to stain the cell and the background, and then the capsule is going to be in between, unstained.
Are you using the same stain for the cell in the background, or is it separate?
Ah, good question. So she asked, are we using the same stain for the background in the cell? What do you think? No, right? What type of stain do we need for the background? Acidic and negative stain, right? Negatively charged stain. What do we need to stain the cell, probably? We need a basic positive stain. So this is a two-step procedure when you do capsule staining. You're going to use an acidic dye and a basic dye or a basic reagent to stain the cell.
Does it matter what order you stain them?
First we'll do the basic, right?
No, believe it or not, first you would stain the background, and then you stain the cell. And actually in that process, the procedure we use even changes the color of the background. So the whole slide changes color. It's really cool.
How does the basic stain enter the cell?
Mm-hmm.
It doesn't stain the capsule.
All right, so the capsule doesn't stain. That doesn't mean stuff can't travel through it. It just doesn't stick to it. And the reason for that is the capsule tends to not have a charge. Right? All our dyes have charges. The capsule doesn't, so nothing's going to stick to it. Stuff will go through it, though. Wow, you guys have got your skills in today. I love these questions. You're really thinking about it. All right, so another problem with bacteria, specifically, a lot of them will have flagella. And maybe you want to see how many flagella and where they're located. Look at this guy. He looks like Scary Cousin It, right? He's covered in flagella. Covered. You wouldn't be able to see that with your light microscope. Because remember, the bacteria are teeny tiny. Never mind some little tiny hair-like appendage, protein, flagella sticking out of it. So we use a special stain called the flagella stain. What this stain does is it specifically sticks to the flagellin proteins that make up the flagella. When it does that, it makes it thicker, so it becomes thick enough that it's within the limit of resolution of our light microscopes. Now, I have to say, I tried. I taught some of the middle school and high school students this summer in our STEM Challenges program. I bought some flagella stain, and I did this stain years ago. We could not get it to work. I was so bummed. We could not get it to work. We don't do it in the microbiology lab normally. We had some slides at one time, and they've since walked away. I need to order us some new ones. But what happens when you stain them and you look at their flagella? You just what? Killed them. So they're not moving anymore, but you can see, that at one time they could move, and why? Because they have flagella. You can see how many and where they're located, but they're dead. You're not moving anymore. Make sense? So again, this stain is going to help us visualize that flagella because it's going to make it thick enough that we can see it within the resolution limits of our light microscope. So for gram stain, I had posted an animation for you. I'm not going to play that one in class, but I am going to go to this website. It's kind of animated, but it doesn't have any audio to it. So of course now it will, because I'm going to add audio to it as we go over the gram stain procedure. So I'm going to introduce this now, and then you guys will continue working on it, and we'll wrap it up next time before we start the next topic. So gram stain. Thank you to the gentleman at North Carolina State for publishing this to the web, because it's really cool. So remember, with gram stain we can get two results. Positive, it stays purple. Negative, it loses the purple and becomes pink. But why? Why do we get these two different results? Why is it purple? Why is it pink? Well, we believe the reasoning behind that has to do with the cell wall differences and structural differences of the cell wall and membranes that gram-negative and gram-positive cells have. So this is a gram-positive cell. You can see the little molecular ID. This is to represent the cell wall, the peptidoglycan layer. Goes away after a second. There's our tictoic acid, which is almost like rebar. It's going to help support this peptidoglycan layer. Talk more about it later. There's our phospholipid and membrane proteins, and these are the dyes we're going to use. Here's the safranin, the crystal violet. This is going to represent the decolorizer, iodine. Come on. And then at one point we're going to form a crystal violet iodine complex. So here you have the cell, you have the cell membrane. All cells have to have a membrane to define it. And then you have this very thick layer of peptidoglycan, this substance that only makes up cell walls of bacteria. So we add the crystal violet. Remember, this is a basic dye, so what charge? Positive. So it's going to go inside, right? It's attracted to the negative components of the membrane, and even inside the cell, the nucleic acid. Then we're going to add the iodine. This is attracted also to the inside of the cell, and will actually bind with the crystal violet and form a much larger complex molecule. The next step is decolorization. The decolorizer we typically use is ethanol instead of acetone, because acetone is damaging to mucous membranes. So we use ethanol, good old alcohol. And what will happen when it's applied is that. What just happened? The cell wall shrunk. Now the cell wall has gaps in it. This allows stuff to get in and out even when the cell is alive. Right? These cells are dead because we're going to heat fix them. We're going to stick them to the slide. We'll talk about that next time. So now the gaps, the holes just became smaller, right? And we've even got a larger molecule. So guess what? Can't get out. It's trapped. So then we're going to stain with safranin. That's a red dye. We stained them purple, they stayed purple, then we stained them red. So what color are they? They're still purple. Because purple is more vibrant than the red, right? So they're going to be a darker purple, but they're going to be purple. Gram negatives, in contrast, have a different structure. They have a cell membrane. If they've got it, a very thin layer of peptidoglycan, and they have an additional membrane called the outer membrane. I like that. That's easy to remember, right? It's the one on the outside. But this one's unique, too, in that it has a layer that's different. This is not phosphates. This is lipopolysaccharide. All right. It's a little bit different molecule that we'll talk about later. So same process, right? Stain with crystal violet, goes inside the cell. Nothing to stop it. The cells are dead. Iodine goes in, binds to the crystal violet. But now this is the differential part. This is what makes differential stains different. Look what happens when we decolorize. Woo. Oh, it compressed the cell wall, but something's missing, right? The outer membrane got deteriorated. Ethanol, y'all, dissolves lipids. This is why those hand sanitizers you use dry out your hands. This is why they're starting to add moisturizers to it so you'll continue to use it. So, shrinkage, but watch. Not enough. Poof. There it goes. So guess what? These cells are what now? They're not stained, are they? They're colorless. So what do we got to do so we can see them? Stain them. So we stain them with safranin. They've been damaged, though, so they don't hold on to a lot of the red. So instead of being bright red, they are pink. 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 Light red. Pink. Okay? So we'll continue along this one. I'll post the next one for you guys as well, right? Because once we finish this one, we'll move on to the next. Make sure you're doing your Connect assignments, right? You need to study up on that first topic and do that assignment.